This works whether the parent population is normal or not. Doesn't matter. This will still work. As long as we have sample sizes of 30, the sampling distribution of the sample mean will be a normal, nice bell curve. Now, if the parent population has a normal distribution, then the sampling distribution of the sample mean has a normal distribution for any sample size. If the parent population is normally distributed in a bell curve already, then we don't even need a sample size of 30. We could take a sample size of 5 or 10, and the sampling distribution of the sample mean would be normally distributed. That'll come up later, just towards the end of class. All right. So I'm going to skip over this slide, and I'm going to go to this slide, and say, remember this town where we had a mean income of 60, median income of 60, mode income of 60? All right, and we want to find the average, the mean population in this town. How are we going to do it? Well, we're going to take a sample of size 30 or more, and we're going to get a sample mean, and it's going to follow the rules that we learned about with the sampling distribution of the sample mean. We can say I'm 68.3% confident that that sample mean is within one standard deviation, etc., etc. And it turns out that even if we go to this town that had a weird distribution, a positively skewed distribution with a bunch of rich people, it had a mean of 80. It turns out that this works as well. This same thing works even though the parent population is not normal. The reason it works is because this still has a mean, and that's all we want to know. We want to know what the mean income in this town is. We don't need to know that it's different from the median and different from the mode. All we need to know is what is the mean. And we're going to ask 30 random people. Maybe we're going to get these poor people, maybe we're going to get some of the really rich people. Sometimes the rich people are not going to be in our sample, sometimes they are. But on average, we're going to get a normal distribution, and it's going to center around the mean of the whole population of 80. So it turns out this works even if the parent population is not normal. Does that make sense? Mm-hmm. And let me go back to this slide. So these three shapes are the parent populations. All right, this is a really weird distribution. This is some town where we've got an equal number of people making, 10,000, 10,001, 10,002, whatever it is. This is a weird where we've got a bunch of rich people, a bunch of poor people, not many people in between. They still have an average. All of these three populations still have an average income, and we want to find out what it is. So let's take a sample size. And let's put it on a frequency distribution. These 9 distributions here, these are sampling distributions of the sample mean. This row is with sample size 2, this row is sample size 5, this row is with sample size 30. So as we take a larger sample size, regardless of the shape of the parent population, the sampling distribution of the sample mean looks normal, is normal. Does that make sense? Okay. Good. So this is going to be our basis for confidence intervals. So because we're able to say I'm 68.3, 95.5, that's going to give us confidence intervals. So we're ready to talk about confidence intervals? You ready? Ready, Lisa?
I'm ready.
All right. So let's look at this example. Suppose we're trying to estimate the average cost of an MBA program in the whole population. We aren't able to research every single MBA program, so we take a simple random sample. We calculate a sample mean of $43,000, and we calculate a standard deviation of the sampling distribution of the sample mean at $2,000. Please state the interval estimate for the average cost of every MBA program use a 95.5% confidence level. So why don't you all start working on that? I'll erase this half of the board. Give us some room to work with.
So, are we using that formula right there? The average is the mean, so it's pretty low, right? Is that the formula that you just erased?
No, you're not gonna need to use the formula. You're just gonna need to use some intuition.
Intuition.
Yes. So, our sample mean is $43,000. Alright, and we have a standard deviation of the sampling distribution of the sample mean at $2,000. So, we want an interval, and this interval estimate is gonna be an amount. It's gonna be like, $41,000 to $46,000. Or, $39,000 to $49,000. It's gonna be a range. And I want you to tell me that you're 95% confident that that range contains the true population mean for the average cost of an MBA program. The 95.5% chance that you've got it right. Anyone think they have an answer here?
What the definition of the sampling distribution, what is it called, the sample, what page is it on? So I can tell.
It's on slide 17. Alright, Andy, help us out. What kind of range would you give us if you wanted to be 95.5% confident? Okay, so what would be the lower end of that range?
Maybe
Wait, aren't we just
go
deducting?
40 or 30, 40?
40?
Because if you're within one standard deviation, it will be less than 41. No?
Okay, so you want two standard deviations.
So
What would be
39,
two standard deviations below 43,000?
39.
I like it. So 39,000 would be the low estimate, and what would be your high estimate?
47.
Okay, 47. Yeah, so this is the answer I'm looking for. So, if we want to be 95.5% confident that we have captured the true population mean, or that this interval contains the true population mean, then we need to go plus or minus 2 standard deviations. What do you think, Charlene?
Go plus.
Well, this is the range, this is the confidence interval. So what you're gonna say to your boss is I'm 95.5% confident that the true cost of an MBA program, the true average cost of an MBA program, is between $39,000 and $47,000. Question, Susan?
So you'd only be 68.3% confident that it would be between 41,000 and 45,000. Okay.
What's your name?
Nadine.
Nadine? Oh, this is your first time here, right?
Late registration.
What's that?
Late registration.
Okay, good to meet you, Nadine. Alright. So, I am 95.5% confident that the true population mean for the cost of an MBA program is between 39,000 and 47,000. And if I wanted to be 68.3, I would do what Susie said. So these are confidence intervals. I think I've got some pictures that might help us. So let's sample for this cost of an MBA program. Alright, let's take a sample mean of size 30. And let's do it not 5,000 times, let's do it 5 times. Each of these little X bars, that's a different sample mean. Okay? If we were to do it 5,000 times, then we would get a distribution that looked like this. Sampling distribution of the sample mean for average MBA cost. Alright, but now someone else has already done that, we're just going to do it 5 times. Alright, our first sample mean, we're going to get, whatever it is, we're going to plus or minus 1 standard deviation. Okay, so does that interval, plus or minus 1 standard deviation, contain the true population mean? The true population mean is the mean of the sampling distribution of the sample mean. So this is sampling distribution of the sample mean, and the center of this equals the true population mean. So the true population mean can be represented with this red line. So I take sample x bar 1, and I get some number, and then I add 1 standard deviation to it and subtract 1 standard deviation to it, and I say to my boss, here's my confidence interval. Does my confidence interval contain the true population mean? Yeah, it does, because it crosses this red line. Okay, so it happens. So what I give my boss is correct. I said I was 68.3% confident, and it so happens, boom, got it. Nailed it. Alright, so I do it again. Or somebody else in the office does it. They do a different sample. And they get x bar 2. They do plus or minus 1 standard deviation. They give this to their boss. They say, I think this contains the true population mean. I'm 68.3% confident of that. Does it?
No.
It does not. Alright, how about number 3? Does it?
Yes.
How about number 4?
Yes.
How about number 5?
No.
No. Okay. So, what are the chances any one of these sample means with plus or minus 1 standard deviation is going to contain the true population mean? 68.3. Yeah. So there's a 68.3% chance that any sample mean would fall in this range. And if you add 1 standard deviation, 68.3% of those times, that interval is going to contain the true population mean. If you want to be a little more confident, then you would make your confidence interval 2 standard deviation y. 2 standard deviation y. 2 standard deviations y. How often is that piece of paper with the range written on it that you give your boss, how often is that going to be correct? 95.5. So just like these. It's like this one's correct, this one's correct, this one's correct, this one's correct, this one's not correct. That only happens 4.5% of the time. And 99.7, if we want to do 3 standard deviations, that works too. Okay, how are you feeling on this? We've got confidence intervals. And we know we base confidence intervals on the sampling distribution of the sample mean. Alright, a couple terms that we already know, that we've already started using, I just want to put them in context. This sample mean, we're going to call that our point estimate. We refer to sample mean as the point estimate for the population mean. So this 9.4, that's our point estimate for population mean. Later we'll do a point estimate for the population standard deviation. We haven't gotten there yet. Rather than settle for this point estimate, we're going to construct a confidence interval. We're going to take this sample mean plus or minus some amount, and we'll call this a confidence interval, and we'll say how confident we are with that interval. Here's our formula for that. Should look somewhat familiar. This x bar, that's the sample mean. This little part right here, what is that? Not the z, don't worry about the z for a minute. Just this part right here, what is that? I can't hear. Francisco?
Is the standard deviation of the population divided by the root square of the sample
Yeah, it is. And what does that equal?
equal to the sample? The standard deviation of a sample mean?
Yes, the standard deviation of the sampling distribution
Sample mean.
Sampling of the sample.
of the sample mean. Okay, so this is our standard deviation metric. It's the standard deviation of this. And we know it's equal to the population mean divided by the square root of the sample size. So we're gonna plus or minus some number of these. Alright, and z is the number of standard deviations. Remember we gave people a z-score last time, so Michael Jordan has a z-score of 2.3. That means he's 2.3 standard deviations above the mean. So if we want to go 1 standard deviation above the mean, we're going to multiply 1 times this. If we want to go 2 standard deviations above the mean, we multiply 2 times this. 2 above, 2 below. We'll maybe do something like that. So that's it. That's it. Let me ask you how we would determine that z value. Let's look at this for a minute. So suppose I want to be 95.5% of my confidence interval. What do I put in for this z value? 2. Outstanding. Let me write that. So 95.5, I put in a z value of 2%. Okay. So we know the rest of it, right? We know the sample mean, we calculate this by sampling for it. And we know how to calculate this, population standard deviation divided by sample size. What if I want to be 68.3% confident? What do I put in for z? 1? Okay, what if I want to be 95% confident? What do I put in for z?
2.
Go ahead, Susie.
1.9 or something, right under 2?
That's the first step, that's the answer I'm looking for. It's something less than 2, right? Because I don't need to be as confident, so I don't need to go as far, so it's something less than 2. In order to get the exact number, we need to look on the z table. And here's how it works when we look on the z table. We say, hey, I need to be 95% confident, so what are the chances of me making a mistake? If I'm 95% confident, what are the chances of me getting it wrong?
4.5? 4.5.
5%.
5%.
5%. So if I'm 95% confident, the chances of me getting it wrong, 5%. Now, there is an equal chance I could get it wrong by being too high or being too low, right? So if I'm 5% chance of getting it wrong, then there's a 2.5% chance of a really, really high frequency of a really, really high sample, and there's a 2.5% chance of a really, really low. So I need the z-score that separates the upper 2.5% from the bottom 97.5%. Alternatively, I could look for the negative z-score that separates the bottom 2.5% from the upper 97.5%. If you look on the graph I gave you last time for class 1, you would need to look here because you only have positive z-scores. So you want the z-score for this, which separates the upper 2.5% from the bottom 97.5. And if you remember, you're going to look in the center of the z-score for 0.975, and you're going to see what z value that is. We're going to give that a shot?
Wait, we're looking for 0.975?
Yes, you're looking in the center for 0.975.
0.835. 0.975.
What's the z value, Susie?
So it falls in between 07 and 08, right, 9.975?
It's not the answer I'm looking for.
And .07.
Go ahead, Lisa.
.18.
0.18?
And
Not the
point-
answer I'm looking for.
One
Eliana?
1.96.
1.96 is the answer I'm looking for. 1.96. So see if you can see 0.975 in the middle and convince yourself how that is going to be a z-score of 1.96. So look at, where's 0.975 in the middle here?
.975.
Okay, 0.9, that's it, 0.975. So that's 1.9 and it's 1.96.
1.96. Oh,
Yep.
that's how you got that number. All right,
Exactly.
thank you.
Exactly, does that make sense, Lisa? You find it?
That's Susie, I'm the
Susie.
second.
Susie, sorry.
No,
Alright, so. So, find 0.975.
right. Is that it? Yeah.
No, that's 0.834.
Oh, okay, I get it. There.
Yes, okay, so
That's
that's
what you're looking at.
1.96.
Right, okay.
Yes. Alright, does it make sense? I'll show you how to read the Z table. Okay. Alright, so great. So this is 1.96. 96. 1.96. Okay. What if we wanted to, let's do one more. What if we wanted to be 90% confident? What would be the Z value we would use for 90% confidence level? So if we need to be 90% confident, what are our chances of getting it wrong?
10%.
10%. What are our chances of getting a really, really high sample mean?
5%.
5%.
And 5% chance of getting really, really high, 5% chance of getting really, really low. So 5% chance of making a mistake down here, 5% chance of making a mistake down here. So I want to know the Z value that separates the upper 5% from the bottom what percent? 95. So the upper 5% from the bottom 95%. So I'm going to look on the Z table for 0.95. Who said that?
1.65.
Yeah, perfect. 1.65 is the correct answer. You feeling okay on this? Alright, let's do an example. Let's look at, on page 248, exercise 7.4. Actually, let me, does anyone, maybe can I, does everyone have their book with them?
I do here.
I can, this is gonna take me a second, I can pull this up online.
You want my book?
Who has their book? Raise your hand if you don't have your book with you. Okay, yeah, let me pull it up online so everyone can see.
Oh.
Okay. So. We want to estimate the average time cars stayed on the lot for these BMW 5280i, these BMWs last year. So, we wanna know how long they stayed on the lot on average. I guess you can't even read that, can you? Can you read that? Oh, sorry. Alright, well. I guess that's the best I
You
can
can
do.
probably zoom in.
I did zoom in. When I zoom in,
Oh, there you
There
go.
you
oh, okay. There we go, sorry about that. Good call, Lisa. Alright, so we want to estimate how much time these cars stay on the lot. Suppose we don't wanna ask every single dealership, because the car dealers just lie to you anyway. We wanna take a sample of 60 BMW dealers, and we wanna figure out, our sample of 60 cars sold last year, and figure out the average time they were sold, and we come up with a sample mean of 97 days. So, we want a confidence interval, 95%, for the average time spent on the lot for every single BMW sold last year, for the entire population. Assume we know the standard deviation for the population to be known at 22 days. How are we going to solve this problem? Let's see if I can. Okay, there it is, you can all see it, but you can't see the answer. So, why don't you start working on the answer? So we got a sample mean of 97. Alright, we know the population standard deviation is 22. Alright, so how do we construct this confidence interval? Someone remind me. Francisco, go
Use
ahead.
the formula.
Use the formula. What's the formula?
It's x bar
Yes.
plus minus.
Plus or minus
2 or the
z, yes, times what?
times the
Standard deviation of the sampling distribution of the sample mean. Okay, so how do we calculate the standard deviation of the sampling distribution of the sample mean?
it's 22 divided by square root of 60.
Yes. So we take 22, the population standard deviation, divided by the square root of the sample size, which is 60, and what do we get? What does that come out to? 2.84. Okay, good. What is the z value we use for 95% confidence?
I'm sorry, what was
What is the z value we use for 95% confidence?
it?
Francisco said 2, and I looked at him like he had 4 heads. 1.96 is the correct answer. Okay, so what do we do next? Well, we take 97 plus or minus 1.96 times 2.84. And what do we get on the low end?
Can you switch over? 'Cause-
Sorry.
Thanks.
On the low end.
Oh, yeah, Susie, you have the low end?
91.4.
You agree, Andy?
I have a question.
Yes.
When you say 95% confidence, you go to the ZTO and look for 95%?
You look for 97.5%. Yeah, so if you're looking for 95% confidence, that means there's a 2.5% chance you could be wrong here.
Okay.
You got it?
Yeah, I got that.
So does anyone agree or disagree with 91.4 on the low end?
With that equation, that's the answer.
Okay, what do you got on the high end?
102.5.
102.56?
Yeah.
Alright, looks good. 91.4 and 102.56. Alright, so how do we present that information to our boss? What do we say? It starts with, I am 95% confident.
That, whatever it is, falls.
That's right, you can, yeah, it's good for now. Whatever it is,
Two
falls.
standard deviations. Within 2 standard deviations of the mean, yeah?
Now, falls within 1.96
Oh, okay.
standard deviations,
96, okay.
and not of the mean. Alright, so,
Of the sample of
okay, so the statement you make, you say I'm 95% confident that the true population mean for all BMWs sold last year is between 91.4 and 102.56. We can stay on that for a while, Eliana, if you didn't like it the first time. I am 95% confident that the true population mean for all BMWs sold last year is between 91.4 and 102.56 days. What do you think, Lisa?
I'm thinking that I need a tutor for this class.
We can work on it. We can
Have
get there.
schedules.
It's so
So,
frustrating, like,
It really is, it's a lot.
I don't even know how to calculate it. I need someone to sit with me and like show me how to do it on a calculator and how to pull these numbers. It just,
well, don't worry about the calculations for right now. Just worry about the intuition. Now, Charlene, this is gonna be tough because you missed the critical part where we figured out how
It's a
to,
piece of lad, sorry.
calculate 1.96. But what we learned while you were gone is that we want 1.96 standard deviations for 95% level of confidence. We want 2 standard deviations for 95.5, which you already knew. But now we know we want 1.96 for 95% confidence. So we took a sample mean of these 60 BMWs and found out the average time they spent on the lot was 97 days. That's our point estimate. If we had to guess, gun to our head, how long do you think the average for every BMW stayed on the lot last year? I'd say 97. Are you with me so far?
Yeah.
That's my estimate for the population mean. The population mean of average time BMW spent on the lot. I guess 97. But that's just one number. I want a range, and I want to be able to say I'm 95% confident that that range contains the true population mean. So that means I need to go plus or minus 2 standard deviations on this sampling distribution of the sample mean. How do I calculate standard deviations on the sampling distribution of the sample mean? I take the population mean divided by the square root of n, and that comes out to 2.84. So,
Wait, can I stop you right there real quick?
Yeah.
When I did that, I got 3.510, so did I do something wrong, 22?
yeah, you did something wrong. I can't do calculator tutoring, so just concentrate on I can do it, I can help you with that after class, but I
Uh-huh.
wouldn't worry about the calculations right now, just make sure you understand the intuition. So, but do you understand, like, how we got that? That's 22, what is this 22? Where do we get that number?
The population,
Population standard deviation, right? And then we divide that by the square root of the sample size. And it came out to 2.84. So we need to go 1.96 of these above and 1.96 of these below our sample mean. And that's gonna give us a range. And we're gonna say we're 95% sure, based on what we know about the sampling distribution of the sample mean, that the true population mean is in that interval. Okay, question? Or is that a thumbs up? Yes. So let's take a break. We deserve it. Let's come back at 8:20.
It's 8:08 right now.
Okay, yes. Let's come back at 8:20. And then we'll do some more examples on the same thing. More examples on this. We're not gonna move on, we'll just try to ingrain this, and we're gonna come back at 8:20.
Look, I got Manhattan.
what?
I went to one today, it's good.
For, is that just for this class?
Go ahead.
No,
Just
it's
like-
right here, right here in track. No, it's on Google, just search for the calculator.
It's
You want me
The
to-
income calculator.
It's everything. Am I supposed to have
Out of bag chips.
Thank you.
Sushi for lunch. I asked him to make me a salad and the stupid jerk was like, oh, we're closing right now. I'm like, I wanna be